So we have a manufacturer of small electric motors who uses an automatic milling machine to produce the slots in the shaft of the motors. A batch of shaft is run and then checked. All shafts in the batch that do not meet dimensional tolerances are discarded, okay? Discarded as scraps. At the beginning of each new batch, the milling machine is readjusted since its cutter head wears slightly during the production of the batch. All right? So if you can visualize the process, that there is this tool that is used to mill the slots in the shaft of the motors. That, if you are using a tool to mill, that there would be a degradation of the cutter as more slots in the shafts of the motors are milled. Okay, so because of the degradation of the cutter, that over time, some of the later on in the production process, some of the shafts that are milled will not be able to meet the required dimensional tolerances and therefore will be discarded as scraps. Okay, and in any production, that is not good because that means that you have cost of producing bad items. At the beginning of each new batch, the milling machine is readjusted, okay? And here, the manufacturer is trying to pick an optimal batch size. What is the best batch size? But in order to do this, he or she must know how the size of the batch affects the number of defective shafts in the batch. Okay, so in this sentence, you see a couple of variables, and the variables are size of the batch and the number of defectives, shafts. All right, so the question for us, the first question in the list down at the bottom, what is the response variable? Okay, in other words, what is the variable of interest in this scenario or this problem, which we again denote as y. So what do you think is the response variable? What does the production manager want to estimate based on the other variable, which is the independent variable?
They're trying to measure the amount of defects.
Say it again. Who was that? Was it Brock? Isaac. Okay. So y, the number of
the number of defects.
Correct. Number of defective shafts produced, and that would be quantitative. So the independent variable then is
the batch size.
Correct. And what is the classification? It's also since both x and y are quantitative, then the appropriate procedure for testing independence is what we call as regression and correlation analysis. All right. But the question is which kind? Is it simple regression or multiple regression? Are we using the simple linear regression or a multiple linear regression? And what is the difference between the two?
It'd be simple.
Okay, who was that?
Kyle.
Kyle?
Kyle.
Thank you. Simple. Why simple, Kyle?
Because there's only one. There's only one of the response variables.
No, there should only be one response variable.
Or one x.
Correct. So that's the important part there, is that there is only one independent variable. If there were two or more independent variables, then we're dealing with multiple regression. Okay, so that's the difference between a simple regression and multiple regression, is in terms of the number of predictor or independent variables. Question 4, what is the regression equation? But once again, before we carry out a regression correlation analysis, there's one step that we need to do, which is, we will call this 4A, generate a scatter plot of X and Y. So we will generate a scatter plot of X and Y. And again, the idea behind generating a scatter plot is so that we can see if, one, there is a correlation or association between X and Y based on the appearance of the plot. So we are going to create a scatter plot of the data set. These two columns here are representing the observed XY pairs of observations, where you have, say, for this batch of 100, they observed 5 defective shafts, right? 125, a size of 125. They observed 10 defective shafts in this batch. Run it again using the same batch size. 6 were observed to be defective. So we will highlight these two columns. Again, this I'm showing you the Excel way where we will insert an XY scatter plot. All right, so here it is. Okay, let me remove the grid lines so you'll just have, you'll just be seeing the pattern that is quite obvious. There's a pattern in the number of defects that are produced by the batch size. And last time I talked about the importance of when you are presenting a graph that you put as much information in the graph as possible so that the graph will speak for itself, right? So we use this quick layout, and you can pick a different layout where you'll have whichever would be best for you. So we will have something like maybe this, right? Where we can change the title, say batch size versus defect rate. And then on the vertical axis, we will replace this with the label of the response variable, or Y. And this would be number of defectives produced. And then on the horizontal axis is the X variable, which is batch size. Now, what is it that you observe in this scatter plot in terms of the kind of the equation or model that would fit in the data set? What happens to the number of defectives produced as batch size gets bigger?
Oh, okay. Okay, now I see it. The bigger the batch size, the greater the number of defectives produced.
That's correct. Okay. So what we can say here is that there is a direct or positive correlation between batch size and the number of defectives produced. Okay, so that's good. So based on a scatter plot, one should be able to give a general observation in terms of how the response variable behaves with respect to the independent variable. So here's another question. If we were to compute or generate the linear equation for this relationship, what would be the sign of the slope of that equation? Will it be positive or negative?
It would be positive.
It would be positive, correct. So we can see that relationship going. Now, going through the steps we did before, all right, so let's just say we've generated the scatter plot of X and Y. Now let's say that, okay, looks like that the relationship between number of defectives in the shaft and batch size maybe kind of follows a linear model expressed by this, all right? So using that, and we're going, again, we are going to test the resulting equation in terms of both the significance and appropriateness. So let us go back to this scatter plot and let us generate a trend line. And I'm using Excel here because Excel will allow us to select a number of trend lines. So just bear with me here, because what I'm going to do is I am going to apply a model that obviously does not fit the data. In other words, a linear model that is not appropriate. Okay, and then we will later on, we will modify this model. So we will use another model that will be more appropriate for the data set. Okay, now I say that the linear model is not appropriate. If you look at this dashed line, that on visual inspection of the plot, that in reality, and we will do this later on, that really what probably would fit more is a non-linear or curved model. Okay, and later on we will develop this curved model. But for now, I want to show that the steps, why we do the steps we follow in regression analysis, especially in determining whether a chosen model is appropriate or not. Let's generate now the regression equation. Okay, let's regenerate this using the data analysis module in Excel. I can now run regression analysis on the data that are presented. Okay, input Y range. The input Y range would be defects all the way down to here. And then input X range would be batch size down to here. I included the labels for the two columns, so I have to select that. And then the output range, let's put that same output in the same worksheet. Maybe over here. And we are going to generate the residual plots and the normal probability plot. Okay, and we said that these plots are going to be used to determine if the chosen model, in this case, the linear model, if it is appropriate for the data. In other words, does it fit the data? Click OK. Okay, so what is the regression equation? And we can pick up that regression equation using here. Okay, let's copy that. And I'm going to paste that down here. All right, so expressing this regression equation in the format here and using the variable names, defects is equal to negative 47.901 plus 0.367x. Okay, so that is the, probably a better way of expressing the linear equation. Oh, and instead of x, I'm going to use the variable name batch size. Here's a question. Based on this equation, for every unit increase in batch size, how many defective units are we going to expect to be produced? So the answer is in this equation.
0.367.
That's correct, Raylene. So you're talking about the slope. Actually, that is the interpretation of the slope of an equation. For every unit increase in batch size, so if you increase batch size by 1 unit, Y defects will increase by 0.367 on average. Okay, thank you. That's also obtained, you can also obtain or build the model based on this. So this is the A, the y-intercept, and this is the slope of the equation. How strong is the correlation between defects and the predictor variable, batch size? And it says use a number and then interpret the value. So what is it that we use as a measure of strength of correlation between variables?
So we would use the R square. Well, that's what we use for the correlation. But then I think Isaac said this one earlier. We would take the square root of R squared.
Correct. So that simply, you'll be using R. So the R, which is the correlation coefficient in this problem, is equal to, it's 0.99764, positive, okay? Why positive? Well, because the slope of the equation is positive. What is the interpretation of this number? How strong is the correlation between defect rate and batch?
It's very strong.
It's very strong. Isaac, okay? Why did you say very strong?
On the diagram that we got,
Uh-huh.
it goes in like increments of 0.5, I believe.
Okay.
And so 0 is like weak or no correlation, and then like
Correct.
some correlation, then anywhere between that is strong correlation.
Okay. So it's very strong, right? So far, this model is looking good by this measure. How about number 6? How much variation in the response variable can be explained by the independent variable? Or in other words, how much variation in defect rate can be explained by batch?
0.9534.
That's correct. Again, keep in mind the R squared value. The R squared value will range from 0 to 1. Okay, if the application you're using expresses the R squared as a proportion, or if it's expressed as a percent, it will range from 0 to 100%. Either way, the R squared value is a measure of the percent of variation or the ratio of variation in the response variable that can be explained by the predictor variable. And we can say, then here's the interpretation of this 95%. 95.3% of the variation in defect can be explained by batch size. That's the interpretation of the R squared value. So in other words, there's not much is unexplained. About 4.7% of the variation in defect rate cannot be accounted for, is not accounted for by batch size. So again, it tells us that this equation here, the linear equation, appears to be very good. Why? Well, the R value is close to 1, and the R squared value is close to 100%.